Let's talk about the acidity of alcohols and phenols for a minute. It says here that a strong base is required to deprotonate an alcohol. Sodium hydride is often used to generate the corresponding alkoxide. And so the conjugate base of an alcohol is called an alkoxide. Here we see that ethanol is being deprotonated by sodium hydride to form sodium ethoxide and hydrogen gas. If we take a look at the pKa of ethanol, its pKa is around 16, whereas the pKa of hydrogen gas is around 36. And since the equilibrium is going to lie to the side of the weaker acid, it is going to lie to the side of the hydrogen gas, and therefore sodium hydride is an efficient base for deprotonating ethanol or any alcohol that we would run into. Another option is to treat an alcohol with a group 1 metal like sodium, potassium, or lithium. When you treat an alcohol like ethanol with a metal like sodium, it ends up producing sodium ethoxide again, and we also again liberate hydrogen gas. You can see that this equation is balanced and that we liberate 1/2 a mole of hydrogen gas for every 1 mole of the ethanol that gets deprotonated. We can qualify the acidity of an alcohol by examining the stability of its conjugate base. If you take a look at an alkoxide that I have shown here, and if you compare it to the conjugate base of an amine, shown here, or the conjugate base of an alkane, well, oxygen is a more electronegative element than nitrogen or carbon, and hence it has a greater ability to stabilize the negative charge, and that's why an alcohol is a stronger acid than an amine or an alkane. However, the halogens have a greater ability to stabilize a negative charge, and hence when we have a halogen, be it fluorine, chlorine, bromine, or iodine, attached to a hydrogen, that's going to have an even lower pKa than an alcohol. It's going to be more acidic. Why? Because the halide is able to stabilize that negative charge even more than an oxygen. So all we're doing is we're examining the atom. If you remember area, we're just looking at the atoms and we're comparing the abilities of the atoms to stabilize the negative charge on the conjugate base. And so you need to know that the acidity of an alcohol is somewhere between 15 and 18. We can see that an amine is somewhere around 35 to 40. An alkane goes all the way up to 50, so between 45 and 50. And of course, the haloacids have low pKa's from -10 to 3. What are some of the factors that affect the acidity of alcohols and phenols? Well, for one, they're affected by resonance. If we take a look at the difference in the pKa's of cyclohexanol and phenol, we see that phenol is 8 orders of magnitude more acidic than cyclohexanol. That means it's 10 to the power of 8 times more acidic than the cyclohexanol. Why would that be? If we draw the conjugate base of cyclohexanol, if that was to get deprotonated, we end up with this alkoxide where we have the negative charge on the oxygen, and that's fine. However, when we draw the conjugate base of phenol, we get what's called a phenoxide, or sometimes we call it a phenolate. And you can see that there's a big difference here because we can draw several resonance contributors. And since that negative charge is stabilized, since it is delocalized throughout the ring, the conjugate base of phenol is more stable than that of cyclohexanol, is the conclusion we would draw. And that is why phenol is a stronger acid than cyclohexanol. It's because of resonance. Another factor that can affect the acidity of an alcohol would be induction. So if we compare the pKa's of ethanol and trichloroethanol, we see that trichloroethanol is about 10,000 times more acidic than ethanol. Why would that be? Well, if we take a quick peek at the conjugate bases, if ethanol was deprotonated, we would get the ethoxide. And if we were to deprotonate trichloroethanol, we end up with this alkoxide where we have 1, 2, 3 chlorines attached to this carbon. Well, what are those chlorines going to do? Via induction, they're going to pull electron density away from the end of the molecule that has the negative charge, and that's going to stabilize this negative charge. And so that is why trichloroethanol is a stronger acid than ethanol. It's because of those electron withdrawing chlorines that stabilize the conjugate base that is formed after it produces, or after you make the alkoxide. Another really interesting factor that can affect the acidity of alcohols is what is known as a solvation effect. And that is exemplified by this example here. If we compare the relative pKs of ethanol and tert-butanol, we see that ethanol is 100 times more acidic than tert-butanol. Now, why would that be? If we think of areo, it's not because of the atom, it's not because of resonance, it's not because of induction, and it's not because of an orbital. There must be some other factor that plays a role here. Well, it's based on what's called solvation. The conjugate base of the tert-butanol is actually less stable. Let's take a look at why that is. If we look at this figure here, it shows the electrostatic potential maps of the ethoxide ion and the tert-butoxide ion. And you can see that since the ethoxide only has an ethyl group on it, it is less sterically hindered, and therefore more solvent molecules can gather around that negative charge, which is shown here by the color red. More solvent molecules can gather around that negative charge to stabilize that negative charge. Whereas with the tert-butoxide, we have much more steric hindrance here around the negative charge, and therefore we can only get a little bit of solvent around that negative charge on our oxygen. And since we have less solvent molecules, it's less stable. And that is why the ethanol is a stronger acid than tert-butanol. Again, the tert-butoxide ion is sterically hindered, is what we say, and not well solvated. Let's take a look at question 12.4, which asks us to draw the alkoxide ion that's formed in each of the following reactions. In the first one, we're taking cyclohexanol and we're treating it with sodium. Well, we know that when we treat it with sodium, we're going to end up producing the alkoxide, and the counterion is going to be the sodium cation. Plus, we also form half a mole of hydrogen gas. In the second example, we're taking 2-butanol and we're treating it with sodium hydride. If we draw the bond between the oxygen and the hydrogen, it enables us to draw the mechanism. We have the sodium hydride, and the hydride ion acts as a base. It removes the proton from the alcohol, and we end up taking the pair of electrons from the bond and putting them on the oxygen to produce the alkoxide. In this case, we also end up with a sodium alkoxide, as we did in the last example. So sodium is our cation, and here we end up with 1 mole of hydrogen gas. Question 12.6 says, for each of the following pairs of alcohols, identify the one that is more acidic and explain your choice. In A, the first compound is going to be more acidic, and the reason why is because of solvation effects. Since this alcohol is less sterically hindered than this alcohol, it is going to enable more solvent to surround the conjugate base and therefore stabilize it. In the second example, we have 2 phenols. However, the one on the left is going to be more acidic, and the reason why is because of induction effects. So we can put here induction, or inductive effects, so we'll put here inductive effects from those chlorines that are on the aromatic ring that would pull electron density away from the aromatic ring and hence stabilize the phenoxide that's formed. In C, this compound is going to be more acidic. Why would that be? It's because both of these are resonance stabilized. However, this compound would have one additional resonance contributor that wouldn't be found in phenol. If we just draw the compound quickly, and we draw the conjugate base like this, we would have an extra resonance contributor where we can move the electrons all the way out to this oxygen on the end, and we can't draw that resonance contributor for phenol. Phenol does have similar resonance contributors, however, it does not have this resonance contributor that I'm drawing right now. So let me finish it like this. And there are other resonance contributors that I'm leaving out, but just to show it quickly, There we go. So we'll put more acidic, and this is due to inductive effects. All right. And for the last one, we have phenol and we have terbutanol. Well, if you remember the pKa of phenol was 10 and the pK of terbutanol was around 18. And so phenol is going to be more acidic, and the reason here is resonance. Resonance. There we go. And I didn't put the reason in the first one, so more acidic. And we'll put here solvation effects.